Okay, in this video we're going to look at some interesting properties of the very, very famous Riemann-Zeta function. So let's recall how it's defined. So it's given by zeta of s, which is the sum as n goes from 1 to infinity of 1 over n to the s power. And I should say that this isn't exactly the definition of the Riemann-Zeta function. The Riemann-Zeta function is some sort of analytic continuation of this sum. But that's not what we're going to go into details today. We're just going to consider it as this sum. And our goals for this video are twofold, and along that goal we will see that we'll construct a nice generating function for the Riemann-Zeta function. And those goals are the following. We want to find the sum as n goes from 1 to infinity of zeta of 2n over 4 to the n. So this is the sum of all of the even values of the Riemann-Zeta function over, obviously, 4 to the n. And then we're also going to find this sum, which is the sum as n goes from 1 to infinity of zeta of 2n minus 1. So this is the sum of all of the even values of the Riemann-Zeta function less 1. And we'll find that both of these sums converge to really, really nice simple numbers. And so before we get working on these goals, let's look at some nice special values of the Riemann-Zeta function. And since we're worried about the even values of the Riemann-Zeta function for our goals, that's what we'll look at over here. So zeta of 2, so that's the sum of the reciprocals of the squares. So there's a bunch of ways to prove that this equals pi squared over 6. This is the famous problem that Euler solved. Zeta of 4, so this is the sum of the reciprocal of the fourth powers of the natural numbers. We have pi to the 4th over 90. Zeta of 6 is pi to the 6 over 945. Zeta of 8 is pi to the 8 over 9,450. Zeta of 10 is pi to the 10 over 93,555. And as a cheeky little joke down here, I have zeta of minus 1 is equal to negative 1 over 12. So this is a really famous internet thing. That's not exactly given by the sum of the natural numbers. That's where this analytic continuation of the Riemann-Zeta function comes in. Notice I didn't include the sum there in this case. Good. And also notice I don't have any odd positive values for the Riemann-Zeta function here, like zeta of 3, zeta of 5, zeta of 7, 9, or so on and so forth. And that's not because they don't converge. They in fact converge by the p-series test, but that's because they don't converge to things that have nice closed forms. So we're not going to talk about those in this video anyway. Alright, so I'm going to clean up the board and then we're going to get towards working on these two goals. Okay, so now we're ready to get started on these goals, and we're going to start with this following very important simple observation, and that is sine of pi x equals 0 when pi times x equals n times pi, where n is an integer. In other words, x must be an integer. So that means the zeros of sine pi x are all integers. Okay, so now we're going to use this fact in order to factor the roots from sine pi x. And we're actually not going to work with sine pi x. We're going to work with sine pi x divided by pi x. So now notice all of the roots of this function are the integers except for 0. We can say that the value of this at x equals 0 is 1, and we can do that using limits. So it's easy to see that the limit of this object as you let x approach 0 is 1. Okay, great. And now let's factor this as well using the fact that all of our roots are non-zero integers. So we have a root which is 1 minus x, one which is 1 plus x, 1 minus x over 2, so that would be x equals 2 being a root, 1 plus x over 2, 1 minus x over 3, and so on and so forth. So now let's check that this works. Notice that this left-hand side and this right-hand side have exactly the same roots. In other words, they have exactly the same zeros. And then also notice that they both have a value of 1 if you plug in x equals 0. So both equal 1 at x equals 0. And essentially, that is the argument to show that the infinite product of sine pi x over pi x is given by this. Okay, so I'm going to clean up the board and then we're going to simplify this a little bit. Okay, so in the last board we argued that these two functions are the same. So we have sine of pi x over pi x is equal to this infinite product. So now what we're going to do is multiply both sides by pi times x, and also we have difference of squares formulas working on each of these pairs of terms over here that we can use. So that's going to give us sine of pi times x equals pi times x, and then those first two are going to multiply together to 1 minus x squared. The second two are going to multiply together to 1 minus x squared over 4. The third two, 1 minus x squared over 9, and so on and so forth. So now we can write this as an infinite product pretty easily as pi times x times the infinite product, n equals 1 to infinity, of 1 minus x squared over n squared. Okay, great. So now I want to rewrite this a little bit. Let's go ahead and write this as pi x times the infinite product, n equals 1 to infinity. And I want to pull out a 1 over n squared out of this and make this n squared minus pi squared over n squared. And so that's the infinite product that I'm going to work with. Okay, so notice now we have sine of pi x equals pi times x times the following infinite product. And so I'll erase that, I'll move that to the board, and we'll work on the next step. Okay, so let's recall on the last board we had sine of pi x equals pi x times the product of n squared minus x squared over n squared. So the next thing that I want to do is take the log of both sides. So notice if we go ahead and take the natural log of both sides, we'll have the natural log of sine of pi x equals the natural log of this product. But then let's just go ahead and recall this super elementary fact that the natural log of a product turns into the sum of the natural logs. So we have natural log of a times b equals natural log of a plus natural log of b, and we're going to use that for these infinitely many terms. And then also we have a similar formula for a quotient, because notice we've got a quotient of terms in there as well. So that's going to give us the natural log of pi x plus the sum, as n goes from 1 to infinity, of the natural log of n squared minus x squared over n squared. So notice that turned my product into a sum. Now the next thing that I want to do is apply natural log rules to the right hand side to further simplify it. So notice that's going to give me natural log of pi plus natural log of x plus the sum n equals 1 to infinity of the natural log of n squared minus x squared minus the natural log of n squared. So I've got something like that going on. Now the next thing that I want to do is take the derivative of both sides. So let's see what we get when we take the derivative of both sides. So using the chain rule over here, we get 1 over sine times pi x, and then the derivative of sine times pi x, which is going to be equal to pi times cosine of pi x. So that's what we get from taking the derivative right here. And now we're going to take the derivative of this right-hand side as well. But since we've done these simplifications with the natural log, this is actually not too bad. So that is a constant. That'll give us 0. And then we get 1 over x plus the sum n equals 1 to infinity, and we can do term by term differentiation here. So notice that's going to give us n squared minus x squared times the derivative of the inside, which is minus 2x, again by using the chain rule. And then over here, this is just a constant again, so the derivative of that is 0. So again, what we have right here is there's our derivative of that term, and there's our derivative of that term. Okay, so next thing to notice is that this is going to be equal to pi times the cotangent of pi x, which gives us a nice simpler formula. We have pi times the cotangent of pi x equals this infinite sum over here. All right, I'm going to clean up the board, bring this to the top, and then we'll move on. Okay, so on the last board we arrived at this formula, which I've cleaned up a little bit and factored some things out. So we had pi times cotangent of pi x equals 1 over x minus 2x times this big sum from n equals 1 to infinity of 1 over n squared minus x squared. Now the next thing that I want to do is use the fact that if you sum from k equals 0 to infinity of u to the k, you get 1 over 1 minus u. And notice we can do something with that sum to turn it into that form. Let's see how that goes. So we can write this as 1 minus x minus 2x times the quantity n equals 1 to infinity, that sum. And then let's factor an n squared out of the denominator. That's going to give us 1 over 1 minus x over n quantity squared. Great. But now notice that this stuff in parentheses looks exactly like this sum of the geometric series with u equals x over n quantity squared. So that means we can turn that stuff in parentheses into an infinite sum itself. So that's going to give us 1 over x minus 2x times the sum n equals 1 to infinity of 1 over n squared. And then we'll take this stuff in parentheses right here, rewrite it with the sum of the geometric series in the following way. So that'll be the sum k equals 0 to infinity of x to the 2k over n to the 2k. Okay, good. Now what we can do is maybe distribute this 1 over n squared inside, and we'll have a double sum. So in other words, we'll have 1 over x minus 2 times x times the sum n equals 1 to infinity, the sum k equals 0 to infinity of x to the 2k all over n to the 2k plus 2. Okay, so let's take this part to the top and then we'll move on to the next step. Okay, so on the last board we had arrived at this formula. We have pi times the cotangent of pi x equals 1 over x minus 2 times x times this double sum. N is going from 1 to infinity. K is going from 0 to infinity. We have x to the 2k over n to the 2k plus 2. So this is starting to look like the Riemann-Zeta function. It looks like we're going to get something like that out of this. So now I want to multiply both sides by x. That'll give me pi times x times cotangent of pi times x on this left-hand side. And then on the right-hand side, I'll have 1 minus 2. I'll have x squared, but I'm going to go ahead and take that inside the double sum. So now I'll have the sum n goes from 1 to infinity, the sum k goes from 0 to infinity of x to the 2k plus 2 over n to the 2k plus 2. Okay, great. Now the next thing I'm going to do is re-index this sum a little bit. So I want to re-index so that k will start at 1 instead of at 0. So in other words, here I'm going to replace k with k minus 1, and that's going to make k start at 1 instead of 0. So let's see what we get if we do that. We have 1 minus twice. Now we have the sum n goes from 1 to infinity, the sum k goes from 1 to infinity, x to the 2k over n to the 2k. Okay, now I'm going to switch the order of my sums. So this is going to give me 1 minus 2, and you can look up some theorems of when we're allowed to do that, but we are allowed to do that in this case. Now we'll have the sum k equals 1 to infinity of x to the 2k. So I'll take the x to the 2k out of that because that only depends on k. And now I have the sum n equals 1 to infinity of 1 over n to the 2k. Okay, great. But now notice what that is. This sum n equals 1 to infinity of 1 over n to the 2k is exactly this Riemann-Zeta function evaluated at 2k. So that gives us this very beautiful formula that we have 1 minus 2 times the sum k equals 1 to infinity of zeta of 2k x to the 2k. So now let's look at our extreme left-hand side of this equation, which is this function that has to do with cotangent, and this extreme right-hand side of the equation, which is essentially a generating function for the even natural number values of the Riemann-Zeta function. Okay, so on the next board, what I'm going to do is I'm going to take this equation and solve for this generating function. I'll just write that down at the top, and then we'll get towards our goals. Okay, so on the last board, we basically derived this formula, which I've just solved and cleaned up. We have the generating function for the even values of the Riemann-Zeta function. In other words, the infinite sum k equals 1 to infinity of zeta of 2k x to the 2k is equal to 1/2 times the quantity 1 minus pi x cotangent pi x. And so now immediately we can attack this first goal, and we can do that by setting x equal to 1/2. So notice that's going to make the left-hand side the sum k equals 1 to infinity of zeta of 2k, and then 1/2 to the 2k, which is the same thing as putting a 4 to the k in the denominator. So that's going to be equal to 1/2 1 minus pi times 1/2 times cotangent of pi over 2. But remember, cotangent is equal to cosine. So we have cosine pi over 2 over sine pi over 2. Now, we know that cosine of pi over 2 is equal to 0. And then sine pi over 2 is equal to 1. So that makes this whole thing equal to 1/2. So that means for this first goal right here, we can just put the number 1/2, and that completes this formula. So now let's go ahead and focus on this second formula. Okay, so now for the second formula, we're going to start with our generating function, and we're going to subtract something from both sides of the equation. So from this left-hand side of the equation, we'll subtract the sum k equals 1 to infinity of x to the 2k. And now notice when we put those together, we'll get something that looks like the left-hand side of this would-be formula that we're deriving. And then we're going to do the same thing to the right-hand side of the equation. But notice that this is a geometric series again, and so we can find the sum of this geometric series. So let's notice that this is a geometric series. The first term is x squared, and then the common ratio is x squared. So that means we're subtracting that from both sides of the equation. So over on this left-hand side, we'll take it to be this sum form, and over on the right hand side we'll take it to be this summed up geometric series form. Okay, so now I'll just insert this in up here so that we'll have a lot of room to work with. Okay, so putting those things into each side of the equation gives us the following. So we have the sum k equals 1 to infinity of zeta 2k minus 1 times x to the 2k is equal to this. So we have x squared over x squared minus 1. So notice I brought the minus sign in and just switched around the denominator. And then we have plus this 1/2 1 minus pi x cotangent pi x term, which we had from before. So now the next thing that I want to do is evaluate this at x equals 1, but notice evaluating it at x equals 1 on the left hand side is perfect. That'll give us our sum identity that we're looking for. Evaluating it on the right hand side is problematic because notice if we plug x equals 1 into this very first term, we will get infinity. We have 1 over 0 essentially. And then notice we also get a 1 over 0 term type over there. So in other words, plugging 0 in here is some sort of infinity minus infinity indeterminate form. So we will plug in x equals 1 into this side of the equation, but what we are really doing is calculating the limit as x approaches 1 of the right-hand side of the equation. So let's reiterate, that means we want the limit as x approaches 1 of, I'm going to bring this half out front of everything, and then see what we need after that. So we'll have half plus x squared over x squared minus 1 minus pi x, and then I'm going to rewrite cotangent as cosine pi x over 2 times sine pi x. Okay, so I've just rewritten that. So notice the 1/2 is no problem at all. We know that that's going to be okay. I'll just take a half out of the entire limit. Now we have the limit as x goes to 1 of. Now what I'm going to do is combine those together into a single fraction. So I'll find my common denominator, which will be this product x squared minus 1 times 2 sine pi x. So that's going to give me 2x squared sine pi x. So that's what we get from the first term. And then minus pi x cubed minus x times cosine of pi x. And all of that is divided by x squared minus 1 times 2 times sine pi x. So what we want to do is calculate that limit. And now I think you'll notice that if you plug x equals 1 into this, we get 0 minus 0 over 0. So in other words, this is an indeterminate form of type 0 over 0. Okay, so now since we have an indeterminate form that's type 0 over 0, we can use L'Hopital's rule. So let's see, that's going to give us 1/2 plus the limit as x approaches 1 of, so now taking the derivative of this numerator, we will get 4x times the sine of pi x, and then that's going to be plus 2x squared times pi times the cosine of pi x, where I had to use the product rule and the chain rule there. And then for my next term, I have, this is going to be minus pi times 3x squared minus 1 cosine pi x. Great. And then I'll have plus pi squared x cubed minus x sine pi x. Okay, so that's kind of a long numerator, and then let's see what we get for the denominator. So we've got to do that as well. So here we will have 4x times sine pi x. So that's taking the derivative of this first term. And then we'll have plus 2 pi x squared minus 1 times cosine of pi x. Okay, now let's see what happens if we plug in x equals 1. So if we plug in x equals 1, here we will get 0. So let's see, this term is 0. Here we're going to get 2 times pi. And then x equals 1 here is another 2 times pi. So notice we'll get 3 minus 1 times pi. Good. And then obviously cosine of pi is, actually cosine of pi is -1, so here we get that. And here we'll get plus 2 pi because it'll cancel with this minus sign. And then over here we'll get a 0. And then in the denominator we also get 0. So we have 0 and 0. So we have another indeterminate form which we'll need to use L'Hopital's rule one more time for. So I'll skip all of those details and I'll just write down what we get when we take the derivative in the numerator and the denominator. Okay, so let's just recall we had an indeterminate form for our limit right here. We do 2 times L'Hopital's rule. I showed all the details for the first time. The second time L'Hopital's rule gives us the following limit. We have 1/2 plus the limit as x goes to 1 of, so look at this numerator. It's quite large and the denominator is also quite large. So let's look at what each of these individual terms are if we plug in x equals 1. So notice x equals 1 here, we are going to get cosine of pi. So cosine of pi is -1, so this is going to give us a -2 pi right here. Then if we plug in 1 in there, we get a 0. If we plug a 1 in for sine, sine of pi is 0, and again, sine of pi is 0. So we have -2 pi in the numerator. Now again, if we plug in x equals 1 here, we're going to get a -8 pi, because again, cosine of pi is -1. Then here we'll get a 0 and a 0 just like we had before. So now putting this all together, we have that this is equal to 1/2, and now we no longer have an indeterminate form, so we're good to go. Notice we have -2 pi over -8 pi, so that's going to be +1/4. So the answer to this is 3/4. So plugging in x equals 1 into the left-hand side, well, that's really like taking the limit as x approaches 1 of the left-hand side, gives us this left-hand side of this identity. And then plugging in x equals 1 to the right-hand side is problematic, but we can do it with a lengthy limit, and that gives us this nice identity here, which is the sum of all of the even values of the Riemann-Zeta function -1 is 3/4. So now we've proven this identity. And that's the end of the video.